Hello, in this lecture we will do a third example on hydrostatics. In the previous examples, in example 1, we used a question in which the structure that we were dealing with was very, very long, infinitely long. In the second example, we used a structure which had elements that were repeating at constant intervals. Now in the third example that deals with a portion of a water tank, of a fresh water tank, we will deal with a case where the length of the retaining structure is defined. So in this question, what you see here is a portion of a water tank which has an opening for an access door, and the access door is attached by 4 bolts, 2 bolts at A and 2 bolts at B, so that is tight and water would not leak around the door or through the door really. Now this is the level of the fresh water, and again a freshwater tank. And let's look, so this is a side view of the tank. Now let's look at the access door seen from the front. So like we were looking from right to left at the side view. So this would be the door seen from the front, and dashed here would be the opening behind it. So this is where the water is in contact with the door, all across this area of the opening. Then we have the 2 bolts at A and at B, so 4 bolts in total. The center line of the opening and the door. And now let's add some dimensions. So distances from the bolt to the center line, 200 millimeters and 200 millimeters. Now distances from the bolt to the edge of the opening, 50 millimeters, both at the top and the bottom, so everything is symmetric really, and 150 millimeters from the center line to the edge of the opening, which of course is 300 millimeters tall and also 300 millimeters wide, so it's a square opening really. The top of the fluid of the water is located 400 millimeters from the center line of the door and of the opening. So again, the left diagram was the side view of the tank, and this is the front view of the access door. Now what we need to calculate in this question is the force in the bolts at A and at B if the tank is filled with water, with fresh water, as shown in the side view diagram. So in order to be able to solve this question, we have to do a free body diagram of the access door. Of course, we have to cut the bolts in order to see the axial force in the bolts, and separate the door from the tank, and then draw all the forces, external forces due to the pressure of the water, and internal forces due to the axial forces in the bolts acting on the door. Now this would be the pressure diagram. Of course, pressure acts only across the door opening where the door is in contact with water, and the pressure intensity of the top is P1, so it's a function of the depth from the top of the fluid to the edge of the top edge of the opening, so that would be 250 millimeters, so P1 is 2.45 kilonewtons per meter square. P2, the pressure intensity at the bottom of the opening. It's calculating in a similar manner, but now the distance is, or the depth is from the top of the fluid to the bottom edge of the opening. So P2 equals to 5.4 kilonewtons per meter square. This is a trapezoidal pressure block, so we can divide it into a rectangular pressure block and the triangular pressure block, and then calculate the equivalent, the equivalent concentrated forces for the two blocks. So for the rectangular block, that is equal to the area of the diagram times the width perpendicular to the screen of the diagram. So that is 300 millimeters, is the width of the opening that is covered by the access door. And we can do the same for the triangular pressure block. The width is the same, 300 millimeters. And these are the magnitudes of the concentrated forces, 221 kilonewtons for the rectangular pressure block and 0.132 kilonewtons for the triangular pressure block. Now we have cut the bolts, so we have to represent the axial force in the bolts. And remember, we have two bolts at A, so hence the total force at A is 2TA. And we also have two bolts at B, so the total force at B is 2 times TB. The location of the pressure concentrated forces and the location of the bolt forces need to be known. And then all we can do is, for example, sum the forces at point A. So getting rid of the unknown TA, and hence the other unknown, the single unknown in this equation is TB, and we can very easily solve for TB, and that would be 97 newtons tension force in each bolt at B. Summing the force now in the horizontal direction would very quickly solve for the axial force in the bolts at A. So therefore, TA will be equal to 80 newtons in tension in each of the bolts at A. Now, is this correct? Well, if we look at these two magnitudes, the force in the bolts at B is larger than the force in the bolts at A, and it makes sense because the pressure intensity at the bottom P2 is larger than the pressure intensity at the top P1. So therefore we expect that the reaction force or the force in the bolts at the bottom be larger than the one at the top. So thank you very much for attending this lecture on fluid statics or hydrostatics.